Hi everyone, welcome to my channel Pure Biology, and today's topic is the logistic growth curve. Okay, this is the logistic growth curve, and already I have explained about the exponential growth curve in my previous video. You just check out that. And before going to this topic, I want to say thank you to all of you who have already subscribed my channel and support me for the growth of this channel. Okay. So today's topic is the logistic growth curve. This is what logistic growth curve, where the populations, in case of the populations of the long-lived organisms, okay, long-lived organism, this type of growth curve is seen. Okay, so here the environmental resistance will come into play. So growth rate can be calculated by this formula. And you just imagine in case of long-lived organisms, the effect of environmental calamities is seen, naturally is seen. But in case of short-lived organisms, there the effect of the natural calamities is seen, but very rarely, because the short-lived animals generally their lifespan is very short. So in that situation, the environmental calamity or environmental impact is not seen properly. But in case of animals, or you can say the individuals, where the lifespan is high or lifespan is more, in that situation the effect of the nature is seen properly. Okay, and in this situation the growth rate that becomes changes. Okay, so here this is the formula. You can see dn dt equals to r dot n k minus n divide sign by k, or you can say by k. So this is the equation. What is that? dn dt equals to r dot n k minus n by k. And this k minus n by k, that is the inverse measure of the environmental resistance. Okay, inverse measure of the environmental resistance. And R is naturally the biotic potential, and K is the carrying capacity. And what is carrying capacity? I already explained in the J-shaped curve, but here I just say you very little or briefly that carrying capacity is nothing but any large term, or you can say that complex term. This is actually the nature fixed it, or the nature fixed the number of animals according to the resource substances or resource materials in a particular habitat. This is called the carrying capacity. If the resource material is very high in that situation or in that habitat, the number of individuals is very high. Okay, or number of individuals you can see maximum. Or in case of where the resource particle is not very high, limited, there the number of individuals also low. Okay, or minimum you can say. So what is the equation? You can see here this is. Now this is actually the logistic growth curve. This is S-shaped and this is just a straight line shape. Okay. So in case of S-shaped and the straight line shaped, it is totally divided into four parts. One is the positive acceleration, second one is the log phase or the logarithm phase or logistic phase you can say, and the third one is the negative acceleration, and the fourth one is the equilibrium. In that situation, the number of individuals stable. No more than individuals will form, or no less than individual will destroy. Okay. So in that situation, equilibrium means the stable situation. Stable. Number of individual is stable. Not more than individual is possible in a particular habitat where the resource substances is generally limited. Clear? So this is the stable. Now, what is saying this positive acceleration? Positive acceleration means the slow growth phase. Here, this portion to this is the slow growth phase. That means the individuals grow very slowly. From there to this is the log phase, okay, or here rapid growth phase is seen. That means the individual's growth is rapid in this part, okay, and this is the negative acceleration, and here the slowing down phase. What is the slowing down phase? That means the growth phase of the individuals that becomes slow, okay, that becomes slow. So this is the negative acceleration, and after that equilibrium, here the stable. I think you can understand it properly. This is the very slow rate phase, this is the speedy rate phase, and this part is where the rate phase again slow down, and this phase is equilibrium. That means the number of individual is stable, not more than individual is possible in that habitat. Okay, so this is the explanation of the logistic growth curve. Now we see this explanation with the help of example. First one, here this is one example. The calculation is that here the k is suppose 100 and n is suppose 50. So in that situation, k minus n by k is 100 minus 50 by 100. This is answer 0.5. What is saying that more number of individual that is less than this. This means more environmental resistance. Clear? More number of individuals is seen. If more number of individual is seen in a particular habitat, the stress by that is applied, not applied, that is stress of the environment is more in that individuals to suppress their number. Okay. And this is the second example where R is 1, N is 100 and K is 500. So in that situation, dNdt is 80. dNdt is 80. So here more number of individuals, that means the number of individuals is 100. In that situation, this is that rises occur up to the positive acceleration, that is the growth phase, and resistance grow to fall the growth phase. What is saying that the dNdt is 80. That means this phase is the growth phase, okay, and this is continuing up to the positive acceleration. This is positive acceleration. Suppose from here to this portion, this is limited by this number of individuals, and after that, so here this is 80. That means after this phase, the number of individuals will increase properly. So what happened in that situation? The environmental impact or environmental effect that create a stress on the individuals. Clear? And this is actually the proper explanation. And we will continue understand, or we will continue we will continually is properly understand how this growth rate is changes with the number of individuals, increasing number of individuals. Clear? This is number of example 2. Now we learn it properly in the following examples. Okay, so let's continue. What happens in the equilibrium situation when the n equals to k? In that situation, n equals to k. When n equals to k, then dNdt, that is growth rate, that becomes 0. You can see here. We just write down here. We have to write in the value of n and k. So here I write down that r dot n, k minus n. This is the formula, and by replacing the n value, I'll just write here k. So what is the answer? That is the 0. That means dNdt or the growth rate is 0. That means the individual remain in the equilibrium situation. Okay. Now here another situation arises, that the addition of the time logs to this equation. Now we have to add the time obviously in that equation, and when we add the time in that equation, the equation totally change from this to this. Just we have to write nt, and here also nt. Okay, the nt is actually the time. Time means we will number of organisms. The within time, number of organisms present in unit time. This is the NT. Okay, this is NT. After that, one situation arises. What is that? The maturity of the all individuals is not occurred in the same time. Okay, is not occurred in the same time. And not only that, they, as the maturity is not seen in all the individual at the same time. That's why they cannot reproduce. All the individuals cannot reproduce at a particular time. So we have to consider this time. We have to write another variable, that is C. Okay, this is called the time log C. This is called the maturity time. Now another situation arises. What is the time, or which unit, on which unit time environmental action is seen on the individuals? That is W. Okay. Now we added all this time with this equation. This is the actual equation. dNdt is R n t minus C k minus n t minus W by k. And you all know that here the dNdt not depends the number of individuals only, that depend on the nt minus C and obviously nt minus W. Okay. Now we learn here this total equation, how this is possible with proper example. Okay. You can see the two examples where the n equals to 450, c equals to 50, w equals to 50 and r equals to 0.6, k equals to 500. In the first equation, the answer is 27, that is the growth rate. In the second equation, when we put the values in the second equation, in that, here the dNdt equals to 24. So, what we concluded that, now what is the actual conclusion of this? That is C and W, the two log time is very important for the growth rate of the individuals. Okay. So, these two are very important. C is the maturity time and W is the actual time when the environmental activity or environmental impact that affects on the individual. So, these are two important time log that affects on the growth rate. Okay, see that. So, today's topic is ended here now. This is the logistic growth curve.